Hello students. So in last lecture of surface chemistry we discussed about distinction of adsorption and absorption, mechanism of adsorption and types of adsorption. Now in this lecture we will start with in detail view of types of adsorption, that means chemisorption and physisorption. So, as discussed earlier, physisorption occurs due to the weak intermolecular attractive forces between adsorbate and adsorbent. That means they are just attracting each other. So, we can assume the example of magnet and iron. So, if we have iron metal, then it will feel attraction towards the magnet, and they are not completely permanently bonded with each other, they are just attracted towards each other. We can put some force to remove them from each other. That means it do not require intense amount of energy, and same type of observation will be done here between adsorbate and adsorbent. As for example, let us assume gas is being adsorbed on the surface of metal. So if it is physisorption, that means they are just attracted towards each other because of residual forces present on the surface of metal. So that's why characteristics of physisorption, first point is mentioned, lack of specificity. That means any gas can be adsorbed on the metal surface without in on depending on its electronic configuration or reactivity. A given surface of adsorbent does not show any preference for a particular gas, as the van der Waals forces are universal. That means any type of gas will feel attraction on the surface. Second, nature of adsorbent. The amount of gas adsorbed by the solid depends on the nature of gas. In general, easily liquefiable gases are readily adsorbed as van der Waals forces are stronger near the critical temperature. So, higher critical temperature, that means at comparatively higher temperature, gases can be liquefied. Critical temperature, that means it is maximum allowed temperature of gas to be in liquid state. So, if critical temperature of gases are high, it represents they have stronger attraction towards each other. That means one gaseous molecule attracts seven second gaseous molecules comparatively strongly. That's why we can easily convert them into liquids. So that represents they have comparatively more attraction towards each other. That means stronger van der Waals forces. So same type of stronger van der Waals forces can be occurred with metals. So thus 1 gram of activated charcoal adsorbs more sulfur dioxide, critical temperature 630, than methane, critical temperature 190, which is still more than 4.5 ml of dihydrogen, critical temperature 33 Kelvin. So as the critical temperature increases, it represents molecules, gaseous molecules are strongly attracted towards each other, or we can say that they are comparatively more polar. So that's why they feel stronger attraction, and eventually they will feel same type of attraction with metals, and more adsorption will occur. Thirdly, reversible nature. So physical adsorption of a gas by a solid is generally reversible. As mentioned earlier, we can assume the example of magnet and metal. So magnet and metal can feel attraction towards each other, and by applying a little force we can separate them. That means it is reversible. So same type of observation will be done here. When gaseous molecule feel attraction towards the solid, they will combine with each other due to the weak attraction. By applying little bit energy, we can separate this, or we can reverse this reaction of adsorption. As mentioned in previous point, adsorption is exothermic process. So exothermic process can be reversed by adding energy. So same type of Le Chatelier principle is mentioned here. Next, surface area of adsorbent. So adsorption is surface phenomenon. So higher the surface, more will be adsorption. So extent of adsorption increases with the increase of surface area of adsorbent, and thus finely divided metal and porous substance have large surface areas and are good adsorbent. And last point, enthalpy of adsorption. So as we know, this is not a permanent bonding, it is weak attraction. So that means enthalpy values will be comparatively low. So no doubt Physisorption is an exothermic process, but its enthalpy of adsorption is quite low, 20 to 40 kilojoules. That means it is maximum up to hydrogen bonding strength. So this is because the attraction between gas molecules and solid surface is only due to the weak van der Waals forces. So due to the van der Waals forces, value of enthalpy will be comparatively low. Okay, so these are the points for Physisorption, and now let us move on Chemisorption. So opposite of Physisorption, it is highly specific because no random gases can form chemical bonding with random metals. Specific type of gases can combine with specific type of metals. That means chemical reaction will occur between them, and as we know, chemical reactions cannot occur randomly. It must be specific. So chemisorption is highly specific, and it will only occur if there is some possibility of chemical bonding between adsorbate and adsorbent. For example, oxygen is adsorbed on the metal by virtue of oxide formation, and hydrogen is adsorbed by the transition metal due to the hydride formation. That means they will combine with each other permanently by forming chemical bondings. So because it forms permanent chemical bond, our second point is it is irreversible. So we cannot obtain initial reactants back by reversing the process because they are completely permanently chemically bonded with each other. As for example, when we place iron metal in open atmosphere, eventually it will rust. That means it will create iron oxide. So initially oxygen will feel adsorption on the surface of iron, and by the chemisorption they will convert in iron oxide, and as we know, we cannot recover it after that. That means you cannot obtain iron metal when it is already rusted. So it is irreversible process. So chemisorption is also an exothermic process, but the process is very slow at low temperature on account of higher energy of activation. So chemical reactions requires comparatively high amount of activation energy. As we discussed earlier, activation energy is the energy requirement to start the reaction. Okay, if we place a glass of petrol on table, it won't start losing energy itself. First you have to activate the energy by providing spark to the petrol. So that means this type of chemical reactions requires higher amount of energy. That's why at lower temperature reaction will be extremely slow. If we increase the temperature, reaction rate or speed will increase. That means it is although exothermic reaction, still with increasing temperature it will increase. So adsorption often increases with the rise of temperature. So physisorption of a gas adsorbed at lower temperature may change into chemisorption at higher temperature. And usually higher pressure is also favorable for chemisorption because higher pressure, that means more concentration of gas, and because of higher concentration of reactant, product will increase. Next thing, surface area. So just like physisorption, chemisorption is also surface phenomenon. So with increasing surface it will increase, and enthalpy of adsorption, as we know, it is chemical reaction. That's why enthalpy of adsorption will be comparatively higher because they are completely permanently bonding with each other via chemical bondings. So table is mentioned. If you have any confusion regarding to this table, comparison table, then you can ask me. Now let us move on adsorption isotherm. Isotherm represents at constant temperature. So here a graph is mentioned. On x-axis we have x upon p, and on y-axis we have x upon m. So what it represents? Here x upon m represents quantity of gas adsorbed on the solid. X represents quantity of gas, M represents quantity of solid. On the surface of solid, X gas will be adsorbed. Now, at variable pressure, with increasing pressure, we can see different type of curves at different temperature. So let us assume we are carry out practical at 273 Kelvin temperature. So as you can see, as we increase the pressure, gas will be adsorbed on the surface of solid, and as we increase the pressure, more and more gas will be adsorbed on the surface of solid. But speed will eventually decrease, and at certain level it will be constant. So that means with pressure, adsorption of gas will increase, but as the reaction proceeds, adsorption rate decreases. So let us discuss it. The variation of in the amount of gas adsorbed by the adsorption with pressure at constant temperature can be expressed by the means of a curve termed as adsorption isotherm. So first is Freundlich adsorption isotherm. So Freundlich in 1909 gave an empirical relationship between quantity of gas adsorbed by unit mass of solid adsorbent and pressure at particular temperature. The relationship can be expressed by the following equation: x upon m is equal to k into p raised to 1 by n, whereas n is greater than 1. So x is the mass of gas adsorbed on the mass m of the adsorbent at pressure p. K and n are constant, and it depends on nature of adsorbent and the gas at particular temperature. So that means these values, constant values, will change with temperature. Okay, they are constant at constant temperature. So relationship is generally represented in the form of curve, whereas mass of the gas adsorbed per gram of the adsorbent is plotted against the pressure. This curve indicates that the fixed pressure, there is a decrease in physical adsorption with increase in temperature. This curve always seems to be approaching saturation at high pressure. That means at different temperature, these points represents saturation point. After this point, if we continuously increase the pressure, adsorption won't change. You will get these type of lines. That means no change in adsorption after certain point. That means saturation point, or we can say that almost full surface of adsorbent is covered. So no surface is left for new molecules to be adsorbed. That's why you will get constant results after certain pressure value. So taking logarithm of whole equation, log x upon m is equal to log k plus 1 upon n log p. Okay, so if we take the logarithm of this value, then you will get this type of straight line graph, and value of slope will be equal to constant 1 by n. Okay, that means you will get value of constant n by plotting this type of graph, and intercept is equal to log k. Okay, so by plotting graph we can get the values of constants mentioned here. So first you have to carry out the practical, and you have to find the value of adsorption of gas on the solid at different pressure, and then we can find the constants value by drawing figure 5.2 Freundlich isotherm graph, and then you can find the values. Okay, so now factor the 1 upon n can have value between 0 and 1, probably range from 0.1 to 0.5. Thus equation 5.2 holds good over a limit range of pressure. That means if we discuss this equation, that means this equation. Okay, so value of n as mentioned, it will be between 0.1 to 0.5. That means it will start from p raised to 1 by 0.1 to p raised to 1 by 0.5. Okay, and large effect of pressure will be observed, but it is not throughout to the wide range of pressure range. That means after certain pressure you won't see any change in adsorption. Initially pressure effect will be observed on the adsorption quantity of the gas on the solid surface, but eventually it will start decreasing, and after certain point you won't see any adsorption with increasing pressure. That means you will get a saturation point after certain limit. So when 1 upon n is equal to 0, x upon m will become constant, and adsorption is independent of pressure. And when 1 upon n is equal to 1, then x upon m is equal to kp. That means x upon m is directly proportional with pressure. The adsorption varies directly with pressure. Both conditions are supported by the experimental results. The experimental isotherm always seems to approach saturation at higher pressure. This cannot be explained by Freundlich isotherm, thus it fails at higher pressure. So what these two situations represent? So our equation is x upon m is equal to k into p raised to 1 by n. So as mentioned, if 1 by n is equal to 0, that means p will become 0, p raised to 0. So it represents p raised to 0 will become 1, and x upon m will become equals to k, and k is constant. So it represents now x upon m value is independent from the pressure. It only depends on constant value k. Second thing, as mentioned in second case, x upon m 1 upon n is equal to 1. So it represents p raised to 1 by 1, because 1 upon n is equal to 1. So p is equal to 1. So it represents our x upon m is equal to kp, and we know that k is constant, so we can say that x upon m is directly proportional with pressure. Okay, but this is true at different conditions. First condition is true when pressure value is comparatively very high, and second term is true when it is low. That means this situation is obtained at high pressure values, and second situation will obtain, that means dependence on pressure will be observed at low pressure values. But we cannot explain this with the help of Freundlich adsorption isotherm. More detail about the effect of pressure on the adsorption is discussed in Langmuir adsorption isotherm. We will discuss about it later.